Okay, so this is about trying to develop a Monte Carlo algorithm to try and speed up the dynamics close to a specific phase transition, which is called the glass transition, which arises in essentially all types of liquids that you know. So because I thought that not everyone would be familiar with the phase transition, there are a few slides about it at the beginning, just to give you a flavor of what it is and what it means, and then I will go into trying to develop efficient Monte Carlo simulations to attack this specific problem. So I start with the physical problem. So the problem is how a liquid, when it's cold, transforms into a glass, such that you can make window glasses, for instance. So you know that for simple mixtures, if you cool a liquid, and try to find the pointer, if you cool the liquid, then okay, so it's very weak. Okay. I'll try to use the two hands. How about this? So I have an idea. I use a pointer and then the keyboard to change the slides, otherwise it's going to be confusing. So this is the pointer, and I'm going to use the keyboard for this. Okay. So if you call a simple liquid, typically what's going to happen is the system is going to transform into a crystal, just like water freezes at 0 degrees into ice. So I will be interested in substances that don't easily crystallize, and as you cool them, they remain a liquid that we call a supercooled liquid, because they don't transform into a crystal. So they remain disordered as in the liquid. And what's happening to them is that as you cool the system more and more, the molecules inside your liquids are moving more and more slowly. And I will show you later how much more slowly they diffuse. And there comes a point where the molecules diffuse so slowly in your experimental in your experiments that the molecules stop essentially diffusing. The particles are completely arrested, and the liquid structure is essentially frozen into an amorphous glass. This is what the window glass is made of. It's a disordered frozen liquid, and the transition point for this is really dependent on how slowly you cool the system. So this glass transition that you would see in an experiment, say when the liquid transforms into a rigid body, it's really set by the competition by how slowly the molecules can diffuse in the system and how fast you're cooling the system. So if you cool very fast the system, you will have a high TG, and if you are very, very patient, then the liquid can still diffuse a little bit, and then you transform into a glass slightly later. So that's the physical phenomenon. You have a liquid that's becoming viscous, more and more viscous. So viscous that at the end it's becoming a real solid. And this is the physical phenomenon that we want to understand. So essentially for you at this stage, the glass is essentially a frozen liquid structure, and it has the property of a solid. So there are many questions that we like to ask about this glass transition phenomenon, about the crystallization, the dynamics of the molecules, etc. I will try and ask just one question today, which is, what would happen if the diffusion of the molecules was not slow, or you could cool the system infinitely slowly, if you wish, to perform an ideal experiment? What would be the fate of this liquid if you cool the system and remain in equilibrium conditions? Would there be a phase transition somewhere? So that's the question that everyone is sort of asking in the field. So why is the question complicated in general? So this is an image of a two-dimensional simulation. I will describe later how these simulations are done. And this is essentially self-propulsive particle that I'm simulating in a two-dimensional space. And I'm rendering each point particle with a sphere to make it a bit more like a physical. So this is a snapshot of a glass. So this system is really completely disordered. It's very dense. Maybe one thing you notice as non-glass expert is that you have large and small particles. Why is that? It's because if you have identical spheres, as you call the system, they would crystallize because the system would be too simple. So one way computer simulators, but also experimentalists are trying to avoid this crystallization and go towards the glass transition, it's just by having a mixture of different sizes for the particles. Of course, in a real experimental system, glasses, you have molecules, they have shapes, so the geometry is more complicated than spheres. But today I'm going to deal with spheres only. So the way to prevent crystallization is to have large and small particles And this type of system doesn't easily crystallize and form this at low temperature. This is a disordered, amorphous, very dense structure. And I can tell you that this guy is very disordered as the liquid that Denis was showing before. It doesn't flow at all. If I push on the part of the system, it's totally like a rigid body. So you may know that the rigidity of a crystal, if you open textbook in solid state physics, it's really emerging from the periodicity of the atoms in the periodic lattice of the crystal. It's totally disordered, and yet it's rigid as a crystal. So this is the question that we would like to address in the context of the glass transition. The further thing that I'm going to introduce later is that I'm showing you here two snapshots of the same pair potential simulated. And with an algorithm that I'm going to describe later, the glass on the right, I think, has been prepared with an equivalent physical timescale, which is about 10 to the 10 times slower. If I probe the physical properties of these two glasses, they're very different. I can tell by the physics that they're too different. By ideal, you cannot tell. So that's the whole question in statistical physics of disordered system. It doesn't look ordered, it doesn't look periodic, it's looking like a mass, it's looking like a high temperature liquid, yet it's a solid with very strange physical behavior, and you can't tell by the eye. You have to be a bit more clever to guess what's happening and how to define the type of phase transition and order that develops at low temperature. So this is the very broad context. So two facts, and the first fact is, of course, critical for what I'm going to say is I've told you that the reason why the system transforms into glass is because the molecules cannot move. So how slow is the motion? And what do we have to fight in the computer simulations in terms of timescales if we want to do computer simulations of the glass transition? So for now, this is an experimental system. So these are real molecules measured by some techniques I don't want to describe. And these people have quantified the logarithm of the relaxation times in seconds for their systems. And this is a log scale here. So you see that essentially they're following the dynamics from 10 to the minus 12 seconds, so picoseconds, the molecular time scale. And the glass transition at low temperature here happens when the relaxation time is about 100 seconds. That means the microscopic time scales of the molecules has grown by a factor which is 10 to the 14 by the time the system reaches the glass transition, in a way that's strongly non-Arrhenius, non-trivial, and that happens for all types of molecules. So this regime is essentially the high temperature boring regime that I don't want to enter, and this is the interesting glassy regime where dynamics is complicated and the particles have trouble to close. And so it means that if you want to reach the beginning of this regime to the experimental glass transition, essentially, you have to follow the dynamics of the molecules that are slowing down by a factor which is gigantic, 10 to the 12. So it means here the experimentalists themselves, they have trouble equilibrating the system, just as computer simulations have trouble equilibrating their systems over different types of timescales. So dynamics is key. And the problem to push these measurements to our lower and lower temperatures is that it's so slow that you cannot wait forever and the system falls out of equilibrium. So the experimentalists in that field are essentially facing the same kinds of problems that simulations have. It means when you go close to the phase transition you want to analyze, the system is too slow, you cannot equilibrate anymore, you're dead, you cannot do any kind of statistical mechanics measure. So to try and describe a little bit what's happening, we believe, or some believe in this field, to the system as it's approaching the glass transition. And again, raising the key question of why it's a hard problem for computer simulations. So this is a well-known historic paper that was published by Kaufman, a chemist 70 years ago. So essentially what he does, he's measuring the entropy of these liquids as they approach the glass transition. And these are different liquids. System is cooling down, and then it hits the glass transition where suddenly the system falls out of equilibrium. So what Kaufman did is he measured some kind of entropy, which he called excess entropy. I'm going to call it configurational entropy. And it's essentially the following quantity. You have the entropy of your equilibrium liquid that you can define and measure. And what Kaufman did, he subtracted the entropy of the corresponding totally ordered phase, which was the crystal at the top. So this is the entropy in excess to the crystal. And what he found is that this entropy is decreasing very rapidly as the system is cooled towards the experimental glass transition. And the key observation of Kautzmann, he said, okay, this is an experiment, and then it stops at TG because molecular motion becomes too slow. But if I could perhaps continue and push these measurements towards lower temperatures that experiment cannot access easily, because again, dynamics is too slow, there is a point where the entropy of the liquid would be equal to the entropy of the crystal. And to him, that was special, because you have a totally disordered phase of matter, which has an entropy which is very low, as low as the perfectly ordered state, which is the periodic crystal. So to him, that was strange that you have a system that's disordered and yet has no entropy at all, at least as low an entropy of the crystal. And that was the hint that something maybe like a phase transition would happen, where the liquid essentially would lose totally its entropy and the system could enter some kind of real ideal glass phase, he called it. And this is this Kautzmann transition that I'm going to try and discuss in the simulations if I have time. I haven't checked when we started. So the question is, okay, this is my experiment. The system is slowing down and then it falls out of equilibrium. It's boring, just a dynamic process. The real question is, if I could perform equilibrium measurements even lower and closer to that, okay, would I discover something like a phase transition there? And at the time of Kautzmann, that really was an extrapolation, a wild one, an interesting one, a hypothesis that has essentially been unproven up to now. So the experimental situation since then has barely evolved, the quantities have been refined, etc. So what I'd like to try and show you is that there are ways to fill this gap between TG and TK now, both in experiments, you probably don't care, but in the computer simulations using Monte Carlo algorithms. And perhaps this is what I want to show you today. Okay. So a little bit about the statistical mechanics of this problem. So I told you it's hard to recognize order when it appears because these glassy states, they look like a bunch of particles put together. It's disordered as a liquid. So what is it that you have to measure if you want to distinguish the glass from the liquid? And that's a problem that I think is fairly well understood from a statistical mechanics viewpoint. So what happened in the last many years, the last 35 years, I would say, that something like a very solid mean field theory for the glass transition has been developed. It started in the mid-80s by studying spin glass disordered models with quench disorder. And I think more recently it gained momentum because the Rome and Paris groups working on statistical physics of disordered systems have shown that if you treat a liquid like the hard sphere system or the Lennard-Jones system or soft spheres, and you take the limit of large dimensions, so really go in the limit of mean field, in the mean field limit in that sense, then the statistical mechanics can be essentially solved and understood precisely in that limit. So it's fairly unphysical if you wish, but at least then you understand and you control the mathematics behind. And then it's becoming what we call now the mean field theory of glasses. And the cool thing about this mean field theory is that, of course, you can do the calculations pretty much exactly. You don't care that the molecules move slow or fast. You do your calculations. And what's happening within mean field, which is very clean, is that it's fairly well understood that a thermodynamic glass transition, as envisioned by Kautzmann 70 years ago, it's exactly realized in that abstract mean field limit. And the nature of the transition is known. It's looking like a first-order transition. And if you wish the corresponding order parameter, what's changing across this phase transition, it's known as well. So I've told you that if you look at a glass, you can't tell whether it's a glass or a liquid. And it's true because it's not by looking at a single density profile that you can distinguish the liquid by the glass. What you have to do is you have to consider pairs of configurations now. And this is what I've tried to sketch here. So here you have a blue configuration and a red configuration. The two configurations are, say, drawn from the equilibrium Boltzmann distribution. And instead of looking at how the blue particles are arranged in space or how the red particles are arranged in space, you do something different. You take that pair and you compare the two configurations. And this overlap, this degree of similarity between one and two configurations, it's essentially done for this, that if the two configurations are essentially uncorrelated, this function is returned as 0. And if the two configurations, red and blue, are very similar, then it returns a number which is close to 1. can define this number like this. In terms of the particle positions in the two configurations, red and blue. And this is what really is capturing the phase transition in the mean field limit. This order parameter, the overlap between pairs of configurations arbitrarily chosen from the equilibrium Boltzmann. It's really the quantity that's changing across the glass transition. So I think I have a sketch of what the phase transition looks like. It's boring. It's looking like an ordinary first order transition for physicists, like first year Mathématiques. And this is the free energy in one of these mean field limits as a function of the overlap that I've just defined. And it has this double shape structure telling you that the system is really crossing a first order transition, just like the liquid gas transition or the Ising model in the field. So the key thing I think that we learn from this mean field theory is the nature of the order parameter, what you have to look in order to distinguish the liquid from the glass. You don't look at configurations, you look at pairs of configurations and you compute their degree of similarity. And this is the structure. So at high temperature, the liquid is the equilibrium phase with an overlap which is 0. You have many different configurations in the liquid. They all look different. So you take a pair at random, the overlap is 0. And the glass is just a metastable phase above the glass transition, becoming the stable phase at the glass transition, the Kauzmann transition. And then it means the overlap is 0 in the liquid and jumps discontinuously at the Kauzmann transition in this mean field limit. A nice quantity that I really like very much is just above the transition. You see that the free energy difference between the equilibrium liquid and the metastable glass, it exists. And this free energy difference, in fact, it turns out it's really very identical to the quantity that Kauzmann has measured, this configurational entropy. So instead of thinking of entropy and order, I think it's better and nicer and simpler and conceptually better defined mathematically to think of this configurational entropy as being simply the free energy difference between the metastable phase and the equilibrium liquid just above the Kauzmann transition. And as you approach the transition, of course, this free energy difference, this configurational entropy vanishes continuously at decay. So this is precisely the scenario that this chemist Kauzmann guessed 70 years ago. He didn't have mean field, but this is, again, exactly realized in mean field. So lots of words for the introduction. So the situation very clear in large dimensions, mean field. We know the phase transition that could be there in 3 dimensions. And of course, the big challenge to theory and simulations experiments is to try to see and understand whether this is true or meaningful or physically appealing in finite dimensions. Because there is no answer. There are many other models in the field. I don't care for. That means it would be cool to have efficient computer simulations to really try and attack this question directly. And this is what I'm going to discuss in a minute. So what about doing Monte Carlo simulations to attack this problem? So I told you one problem that if you simulate the physical dynamics, it's slow. So how do you make better simulations? You have only 2 ways. Either you wait way longer because you have better computers, you parallelize, you use GPU, so you do the brute force equilibration closer to the transition. That's one way I'm going to discuss. Or you try to find a way to bypass the slowing down associated with the phase transition. And this is what smart Monte Carlo simulations are about. I told you the experimentalists are facing the exact same problem, that they are limited in their timescales, much less limited than simulations, but they are limited. So people in experiments do the brute force equilibration, and they have studied these geological ages, glasses, for instance. So this guy is about 10 million years old. So it means an increase in the timescale of the experiment by a factor of 10 to the 8, which is gigantic in a sense. And so brute force can be used for experimentalists, okay? And they have used it. They also found smarter ways of preparing glaciers that I won't describe totally today, by this process where you slowly deposit the molecules on top of the substrate and you grow the glass from the vapor directly. It's been discovered just 10 years ago by my colleague Mark Ediger. And again, it turns out after many years of studies of these materials that it's looking like a smart Monte Carlo thing. You do in an afternoon something that would have taken a million years produced by just normal ordinary cooling. So it's a smart way to bypass the dynamic slowdown, and they do it. And again, the speed up they get is a factor something like 10 to the 8, 10 to the 10. So it means by this process, experimentalists can really try and go deeper below the conventional glass transition. So this is what we'll try and do in computer simulation. So what can you do with brute force computer simulations? If you want to be very efficient, you have to be very simple in the way you describe the liquid. And this is typically what we do. So we take pair potentials, classical, and we simply describe the particles as being off-lattice point objects with some kind of interactions between them, hard spheres or Lennard-Jones or whatever. But the simpler for me is always the better. And I told you that if you want to prevent this crystallization that would arise in monodispersed, say, hard sphere fluid, as we heard before, you have to take at least 2 sizes or 3 sizes or a continuous distribution of sizes, and that is preventing the system. So if you do ordinary simulations, so you would do molecular dynamics to simulate, say, atoms or molecules. And if you're interested in colloidal physics, you would simulate instead Brownian dynamics. And so the algorithm is simple. You discretize the Newton's equations, and then you integrate, and that's it. So in terms of what can be done by this type of approaches, is it started maybe 30 or 40 years ago already. And how many decades, how many time steps can you do? It has evolved over the years. So from 2 decades at the beginning in the 80s to 5, 6 interesting decades of glassy physics. So I told you at the beginning that in experiments to reach TG, you need 12 decades. So if you can do 5 or 6, then you're still 8 decades short with respect to conventional glasses. So simulations are hard, much harder than experiments by something like 10 to the 8. And of course, I told you about these new types of glasses that add a factor of 10 to the 6 or 10 to the 8. The gap between these newly prepared glasses and conventional simulation is 10 to the 14. So it's gigantic, so it seems hopeless. This is just historic images. This is a computer simulation from the end of the 90s. So look at the range of timescale they were simulated, something like 4 orders of magnitude. And this is a time correlation function, which is capturing how slowly the particles diffuse. And the range of growth of this timescale is a factor which is 2 or 3. So it's really the beginning of computer simulations. So this paper has been cited hundreds, maybe thousands of times. So it's a binary Lennard-Jones system. And here you see that the range has grown because computers have been developed. And so they can simulate something like 7 orders of magnitude. And the increase in the relaxation time is something like 4 orders of magnitude. Okay, so still short of the 12 I showed you. And this is, I think, a hard sphere system in 3 dimensions. So you see it 2009. It's about 9 orders of magnitude, and the increase of the relaxation time is maybe 6 orders of magnitude. And for hard spheres, which is the simplest of all. Okay? So this is what can be done due to the progress of the hardware. And this is where I think Monte Carlo simulations can help and do something. So what can you do in terms of a simple Monte Carlo approach to the problem? Well, you do the simplest you can do. You do the traditional Monte Carlo for off-lattice fluids, which I think was described at the beginning. So you pick one particle at random, you try to move it a little bit, you apply your metropolis, and then you satisfy detail balance. And then you repeat. And then what can you optimize? Almost nothing. The only thing you can optimize is how big is the random displacement you give to the particle, and that's it. So when you do this, you find your optimum, you simulate, and this is, I think, how these hard sphere simulations were done. And so what you find as a result of this Monte Carlo simulation is that if you look at a typical time correlation function, again in log scale, it's essentially looking like what molecular dynamics does, apart from, of course, an adjustment of the time scale. But the long time dynamics of this is essentially the same. So it means how the particles move at long time and relax in this dense metric. It doesn't care about what the actual microscopic dynamics of the particles are. Moreover, if you measure this relaxation time and you measure its evolution as a function of temperature in molecular dynamics or Monte Carlo simulations, they track each other perfectly well with no temperature-dependent factor. So it's telling you something. It's telling you that you can replace molecular dynamics by this simple Monte Carlo algorithm. It's nice because it's reproducing the physical dynamics quite well. but it means that essentially the slowing down is the same. So in terms of, if you're looking at efficiency of the algorithm, you're dead because the Monte Carlo algorithm, in that way, is just as slow as the molecular dynamics itself. So it's interesting, you can do the physics, but you cannot speed up the dynamics. So that's the trade-off. So it's a physical algorithm, but it's not smart in the way I've described before. So what can you do if you want to be smart? Well, you look on the market, what's available, and then you try and apply all the tools that Monte Carlo simulators and smart Monte Carlo simulations have given us to study systems with complicated features. The first thing that people have tried a lot in the context of disordered spin systems are these parallel tempering, where you have a chain of temperature and you try and move and climb this chain. It hasn't been very much studied for glassy liquids, but the gain is rather modest, a factor maybe 100, even though I had to guess that number because it was not quoted in the papers I read. We're going to hear something about population annealing, which is a different kind of parallel tempering to me. And John Mashta in UMass has published papers interesting about this method in the context of glassy physics. I cannot tell the gain that they have, whether there is a gain at all, by the way. Something called Wang-Landau again, which is to explore phase transition, has essentially not been tried for glassy fluids, which could be tried. Juan de Palvo did something, but it's really hard to understand whether it gives some. Interestingly, the event chain Monte Carlo that we had in the previous talks and probably other talks has been used just a little bit in the context of glassy physics, a lot in the context of monodispersed systems. Not so much in terms of glassy physics. There is a paper by one of Werner Kraut's collaborators, Isobé, and the factor, as I can read from the paper, is something like a factor 40 of speed up, but really I'm not too sure whether it's correct or not. And this factor. So the speed up of the event chain, I don't know, and it's bad that nobody has tried that before. So I'm going to describe a smart Monte Carlo that looks totally stupid, actually. So it's called the swap Monte Carlo algorithm, and it does the following thing. So you define the probability P, and with this probability P, you did the translational moves I told you about before. You pick one particle, you try to make a small displacement, and you accept, reject with the metropolis. So that's ordinary, simple Monte Carlo simulation. And then the interesting bit, the new bit comes with the probability 1 minus P. The other types of moves that you do is just the generalization of one particle move. You pick up two particles at random. So you take two particles at random in the system, and you attempt to swap their identity. And that's it. So it's a two-particle move where you just move and exchange the positions of two particles. So that has been first tried seriously in the context of glass physics by Grigera and Parisi many years ago. And then their co-workers have tried and quantified in one paper the speed up they get. And in this paper, they say the speed up is about 200, and it's not temperature dependent. So it didn't look so promising at the time. And then Dave Reichman at Columbia tried it on different types of glass systems, and they all crystallized easily. So he said, okay, not only it's not super fast, but on top of it, it's crystallizing everything. So it's boring. So essentially, research stopped. And so what I think was the surprise to us is that if you push and think just a little bit about the swap Monte Carlo algorithm, first of all, you can forget about crystallization by thinking harder about the types of particle and size distribution that you chose. And we have worked very hard, well, actually my student Andrea Ninarello worked hard to really develop models for which crystallization was no longer an issue. So we could concentrate on the speed up now because we could go and forget about the crystal. And this is one of the best examples that Andrea Ninarello got in his thesis. So this is a measure of the equilibration time for one of these three-dimensional subsphere systems that we like to simulate in the system. And this is what the physical dynamics does, either Monte Carlo or MD, because they track each other. And I told you you can simulate something like 5 to 6 orders of magnitude of the growth of this relaxation time. So if you want to reach the expander glass transition, you really have to fill that gap of 7 or 8 orders of magnitude to reach this 10 to the 12 that defines the expander glass transition. So what the swap Monte Carlo algorithm does for this, it's doing this. If you measure the equilibration time in the presence of the swap move that I just defined, you take pairs of particles and you simply exchange a big particle with a small one. This is the equilibration time of the system. So swap does nothing in the boring high temperature non-glassy system. But as the physical dynamics slows down, the swap almost doesn't slow. That means by the time you reach this segmental glass transition that you never get by the physical dynamic, the swap relaxes in something like 10 to the 2. That means at TG, the speed up in equilibration time is something like 10 to the 10. And swap can be pushed even below the exponential glass transition, even lower temperature, where the relaxation time would be even larger. And then it's your guess to guess the efficiency or the speed up of the algorithm. But at the very least, it's more than a factor 10 to the 10 of speed up in equilibration in 3 dimensions for different types of systems. In 2 dimensions, it's even more. I mean, we can simulate the swap very longer, and the physical dynamic shoots up dramatically. And we try to put numbers just to get a figure, and the speed up is larger than 10. Essentially, the simple, stupid 2-particle move is killing the glassy dynamics almost completely in 2 dimensions. So that, I think, is the point of the talk. So I'm trying to figure out the how much time do I have? So what does it do? Well, I said it's a smart algorithm that looks totally stupid. So why does it work at all? I think it's still a little bit of a mystery. I'm trying to argue and give you some flavor for it. So first of all, I think one reason people have not really tried hard enough to invent smart Monte Carlo algorithm like many particle moves, that there was something in the head of everybody, including me, that if the dynamics is complicated, correlated, cooperative, we're approaching a glass transition, then it's probably going to require non-local Monte Carlo moves, like giant clusters being moved together. And I told you, if you look at the system, it's looking like a stupid, boring liquid. So what do you move? What are the clusters to be moved? I mean, for Ising models, we know what are the clusters because we know the magnetization and everything. So people thought we don't know what the clusters are. It's hard to decide. So how do you even try that? In a sense, the efficiency of the swap, which is a 2-particle thing, which is very local, it's a bit unexpected from theoretical ground, which means it has led to very, very interesting debates about the nature of glassy dynamics since the success of the swap. So one way to think about the physics of why the swap is working so well is to think in terms of so I think I showed you the sketch here. So the way I've described is you take one particle and you make it translate elsewhere. So one way I like better to think about the swap algorithm is to consider this blue particle. It's a big one. It's going to swap the identity with this one, which is a small one. What I like to think is that this guy is not really jumping to the other place. It's staying there, but its diameter is changed. So it's as if the diameter of the particle was now becoming a dynamic variable. And this is how I like to think about it, because then in the simulations, especially if you have a continuous distribution of sizes in your system, it means the diameter of a given particle is becoming a dynamic variable now. And it means in terms of what are the degrees of freedom attached to a particle, you have x, y, z, the positions, and now you add sigma, the diameter, which is changing as well. So the system is trying to diffuse. It's hard, but the diameter is changing at the same time. And I think what's happening really is some kind of coupling between this new degree of freedom, the diameter, and the position. And the diameter is helping the positions, and the position is helping the diameter. They are strongly coupled. So we looked at time series of displacements and diameters for many, many particles. It's not totally clear what's happening, meaning it's complicated. So there are cases where the diameter is changing a lot and the position is changing a lot at the same time. So you say, okay, the particles become small and then it has space to move. But it's not always the case. There are cases where, like here, where the particle suddenly becomes small and it doesn't move at all. So it means it's not a single particle thing, like you have a small mouse and it goes small to go through the hole. It's not like this. It's a complicated collective things where you have a coupling between diffusion in diameter space and position space, and this is what's speeding up the dynamics. So it means adding one more degree of freedom was the key to really unlock and solve and speed up the equilibration. So the only idea that comes to my mind is, can we add 2 or 3 or 5 more degrees of freedom and go even better and have an even better improved swap Monte Carlo algorithm? I've tried and failed many things, but maybe I'll find an idea later. So I think I'll start with the Monte Carlo itself. So what are the new things that still, I told you about the failure, try to make it better. It's already very good, so I've played a lot with it in the last 2 years. One thing we did is we wanted to really try and make the connection with this mean field theory that I mentioned before. And so one direction that we have explored is, can you generalize the swap algorithm in dimensions that are getting large and large and large to go toward this mean field limit that has been solved exactly, and see whether the physics there and the physics in 2-3 dimensions could be smoothly connected. And the swap, for instance, in 4 dimensions, it's giving us a gigantic speedup. Up to 8 dimensions, it's still giving us lots of speedup. One other thing we've done is we try to come back to molecular dynamics, more continuous time-like dynamics. We've done 2 things. We've done a hybrid molecular dynamics, Monte Carlo dynamics, where we do the translations with ordinary molecular dynamics, and then we do the swap moves with Monte Carlo. So we've tried this, we've implemented in the packages that people use in the field, and it works just as well. We even tried to develop a totally continuous dynamics, so pure molecular dynamics, where the diameter and the positions now evolve through some kinds of Newton's equations of motion. And again, this swap MD and the swap MC, they agree fully. So you see the same types of speedup for all types. Just for the physical dynamics, where molecular dynamics and Monte Carlo give the same physics, it's also of the swap. If you include the diameter, you can forget about doing Monte Carlo. What really matters is the fact that the diameters are really moving. Maybe I'm going to finish this because of the time. So we started with hard spheres, self-repulsive spheres, then we went into Lennard-Jones systems, and this is what I showed you. I want to show in this final slide, probably. So the system that has been simulated hundreds of times, it's called the binary Cobb-Anderson. It's a mixture of 2 Lennard-Jones particles, and that's the canonical model in the field of the glass transition. It turns out that the A and the B particles of this mixture, they are so different that if you try to swap them, the metropolis kills everything. So you cannot swap the binary Cobb-Andersons. So we thought, okay, how do we invent a model that's looking like the Cobb-Anderson, but you can do the swap moves? And so we just said, well, let's introduce an intermediate species in the middle, so the C species, which is halfway between A and B. And we did that, and it turns out that the swap between A and intermediate C particles are allowed. The swaps between B and C are allowed. So it means in 2 swaps, you can jump from A to C and then C to B. And then you have done your swap from A to B. That's impossible otherwise. So we've developed ternary or even continuous things with the Lennard-Jones, and we get, again, gigantic speedups. And these systems are actually good representations of actual materials called the metallic classes. So maybe that will be my conclusion. One direction I'd like to explore in the future is that if you look at real glasses, they're not hard spheres, they're not Lennard-Jones. They're complicated objects, they're molecules, for instance. So how do you swap moves with molecules? How do you swap moves with something that looks like polymer glasses, polymer chains? And this is really something that I would like to study in the future. So I had a part, I think, about applications of the swap to address the key questions in the field regarding the Kaufman transition. I know it's over. I have 1 minute. So if I sketch what the big picture comes is, we've done swap Monte Carlo simulations in 2 dimensions and 3 dimensions. We've measured tons of quantities that we get or got from this mean field approach, these free energy measurements, this configurational entropy. When we put everything together, we use the swap that allows us to go very, very close, I would say, to the Kaufman transition, the putative Kaufman transition. This is, I think, the best extrapolation that comes from the simulations. I told you in 2 dimensions, we can go very low in temperature, and we find nothing like a phase transition down to 0 temperature, and it all extrapolates to a 0 temperature critical point. if you do 3 dimensions and we do tons of extrapolation from different directions, we have a very strong, I think, support for the idea that a phase transition like the one envisioned by Kurtzman and then predicted by mean theory exists in 3 dimensions, suggesting that 2 and 3 dimensions are different, and maybe 2 would be something like the lower critical dimension. And all this comes really from applying and using the swap Monte Carlo algorithm to the thermodynamics behavior of this system. And just one image to finish, maybe. So I've shown you this swap move, which is 2 pairs of particles. If you look at what the particles do really in computer simulations, they do complicated things like this. So clearly doing something like more collective moves. I don't know whether these are chains or something, but these are the physical moves that the particles do in order to relax in the dynamics. What I think would be really nice for me is, can we learn from the system itself what are the real Monte Carlo moves that are needed to speed up the dynamics considerably? For instance, using tools for machine learning would be nice. Thank you very much.
Okay, front row. Thank you very much for this very nice talk. This very interesting diffusion in diameter space, is this dependent on a hard sphere interaction, or can it be generalized to any form of interaction?
No, I mean, we've... no, it doesn't depend at all. So it's a way of describing the swap dynamics, the way that you can do the swap dynamics with whatever pair potential you like, provided you find, the distribution of interactions that allow for the swap mode. Some models you can't, you can't swap because the particles are too different. Okay. So you have to play a little bit with the model so that at least some swaps are accepted. But when they are accepted, then the diameter is changing with time.
Yeah, also a technical question of some sort. So when you choose the swap partner, is that done uniformly at random, or is there any scope for actually playing around there with having more local swaps or stuff like that?
So the only thing we tried is we tried to, instead of taking 2 particles at random, then by definition they are far away, we tried to swap, neighboring particles, or having a range for the swapping pair. Doesn't change a thing, it seems. So, and in the version where we do the diameter dynamics, really we do it with the reservoir, so it's a totally local thing. And so it means, it seems that really what matters is that the diameter is changing. It's not really how you change it and with whom you exchange the diameter. That doesn't seem to be playing a role.
Right, thank you.
Any other question? I just have one, and because I'm the chair, I'm taking the time. Do you have some limitation on the system you can actually look at, meaning like in the distribution of the diameters in your system?
What kind of limitation do you have in mind?
Like you have the radius, like you have some, for instance, 2 species, and the radius are kind of close together or very different.
Well, we have 2 constraints. I told you that if you make say you take a mixture of 2 sizes and you make the 2 sizes very close, then of course it's very easy to swap because the particles are almost identical. But then the system is almost monodispersed, so it's going to be very unstable towards crystallization. It means we need large, size ratios to prevent the crystallization, and at the same time we need small ones to help the swap. So this is why we went first to the continuous polydispersity, because then at the same time you have diameters that are very different, and you always find pairs where the diameters are not too dissimilar, and then the swap works. And then we made it into like 4 components, 5 components, and then you have discrete. So it's a discrete version of the continuously polydispersed. It all works. Of course, if you want to simulate, say, a real material, say copper, zirconium, zinc, whatever the metallic glass people like to do in the experiment, then you cannot play around with the diameter. They are given by the atoms you want. So it means for some real material, the swap is going to work because the atoms will be close. And for some system, it will be totally impossible to use because the atoms will be too dense. So that's one limitation.